So we've just finished installing the nozzles for the Turborocket Mark 6. Here they are. You can see them in all their glory, oriented in the correct position. But to get to this state required some amount of work, and so I thought it might be useful to kind of show you the process by which we fabricate these nozzle inserts and then install them into the Turborocket combustor head here. So in the next couple of vignettes, we'll show you the details of that process. So to fabricate the nozzle inserts that we use for our Turborocket engine, it begins by using a blank, which we, in this particular case, are these half 20, 20 is a UNF for this size, half-inch UNF 20 stainless steel bolts. So we begin with these as our blank, and then we machine these down into the proper shape that can be used for our nozzle inserts. That also applies to the hold-down nuts on the outside. We use just an 18/8 UNF 20 nut as well, and then those are machined down to make our components, the nozzle insert, and then the retaining nut on the back side. And so I like 18/8. It's reasonably high temperature and it machines pretty well, and it's modestly priced too. So in the following videos, we'll show you some of the machining operations as we create these nozzle inserts, starting with our nut and bolt blanks. So here we are machining our quarter 20 bolts down to the size they're going to be in the nozzle. So we just set it up in the lathe here, and we're just knocking back these, the basic shape here. Come off, we come off, a few thousand at a throw here, and just kind of easily trimming it down. The 18/8 trims real nice. And so we're going to trim this on down, and you'll see kind of what it looks like. So we're going to trim down. We'll make it round, kind of like our other nozzles, and get those all trimmed down. And then we'll have some that we'll be able to set up and use for the rest of for when we put in our fixture, so they can trim the angle, the nozzle angle into the device, into the little nozzle insert. So after we have completed machining our blank down from our 18/8 half 20 bolt, then we're ready to put the hole in it at the correct beta angle. And so I tried several different approaches to orient this correctly. And the approach that I came up with was to first generate a 3D printed plastic, PLA plastic sort of tool holder that I can make the holder blank in. And so this sits in the lathe at the orthogonal to the lathe, but inside, I don't know if you can kind of see it in there, is the you can see that there's a cylindrical surface that is set at the beta angle. You can kind of see it, that edge over there is a little taller than if we have it over here. And so that allows the tool holding blank that we're going to make to sit at the correct angle. Then we machine a piece of aluminum that fits down in there at the correct beta angle. So when we do that, then we can clamp this assembly, the blank, before the hole is put in, with the plastic in the lathe, and then plunge the hole in that is the diameter of the nozzle blank, and then it's set at the correct angle. So we've used a tool holder to make another tool holder. So the plastic just doesn't take the temperature as well. It's not a high temperature loading when we put this hole in, but when we go to put the when we go to put the hole in the stainless steel blank, the temperatures get a little bit warmer, and so having a metal tool holder for that makes that possible. So here's the tool holder for the nozzle blank, and it's at the correct beta angle. Kind of see it down in there. And then I've cut some slots in it that allow the edges to these segments to flex a little bit and grip onto the nozzle blank. So that fits in there. Then this goes into the lathe, and then we can perform the plunge operation to put the holes on the nozzle throat in. The scarfing operation first to get the surface at the correct angle. The hole goes normal to that surface, and then we also make the nozzle expansion. So now here's our fabrication technique for the nozzles that have a particular beta angle. As you can see, we've made a fixture that has the proper angle cut into it, and it's aluminum so that it can kind of take the heat from the machining operations. We shouldn't need that, but it's just a good practice and better. It's going to give us better performance. So we're doing the machining operations, and you can kind of see that there's a little spacer there that is at the angle. We 3D printed that so that there's a little bit of a beveled washer, if you will, or a spacer that puts everything at the correct angle, just so that it stays flat against the surfaces for the part. And we've put in our holes, and so when it is at an angle and we're drilling relative to, and we're doing a machining operation here, when we do a lathe cut, it makes the surface orthogonal to makes it flat against the axis of rotation. And that's kind of what we want, so we don't have any scarping on the nozzle. We've just finished putting in our holes, and then we've also, in addition to putting in the holes, we've put in our taper or expansion on the hole using the 15-degree total subtended angle, which is a standard angle for nozzles. So we just use that to put in the taper or the expansion on the nozzle. So this nozzle has a 0.21 inch throat diameter that we just drilled out, and then it expands out to 0.25 inches. So not a huge expansion ratio. We don't have a high pressure ratio here, but that's how we do the machining operation to make these nozzles that have a relatively small beta angle. And these are designed for 3 degrees beta angle, so pretty small. And so that's how that's set up. You'll also note that we have these index marks shown here, which show the direction of the lean. So the nozzle is rotated towards that mark. So that's how you know which direction the nozzle is leaning when you install it. So we'll go ahead and make the other one, and that's what we're doing. Okay, now we're installing our new nozzles. We've just finished fabricating. This is the outlet end. This is the inlet end. So we're going to be putting the nozzle inserts into the chamber of the Turborocket Mark 6 unit, and then we'll use to seal them. We'll use a high temperature RTV on these and see how it works. It might exceed the temperature, but this will be our experiment to see how well it works. The temperature actually of the gases in here may be lower than what we're going to see here because of the nature of our propellants, but it'll be part of our experimental testing. So these nozzles go in here as an insert, and there's a step on them, and that seals against the inside surface of the combustion chamber. And then on the back side here, we have these nuts that we'll be using to cinch down on the forward face of the nozzle insert. And we'll use a little of this anti-seize, high temperature anti-seize compound to make sure that we can get the nuts off after the testing. So let's go ahead and get that process started. We'll begin by applying a little RTV, this high temperature RTV, to the sealing surface on our nozzle inserts. Okay, so we've got our RTV on our nozzle insert, and now we'll slide it into the element there. We've got the other one already in there, and it's doing fine and going through there, but we'll go ahead and slide this one on through. I will say that I much prefer to use an O-ring or some sort of a seal rather than slathering on an RTV, but in this case we kind of need to do it this way, and so we're going to continue to use this process. It's kind of a one-off kind of thing, but it'll work well enough based on my previous experience, but we'll try to move to an O-ring based solution at some point. Okay, now we have both of our nozzles sort of glued in there, if you will, by this RTV. They're kind of RTV'd in there. And now we're going to apply the anti-seize compound to our nuts to hold them up against the face. These are more just to kind of hold them up there. They're not really load bearing, but they do, because the pressure is pushing out on the nozzles. But we'll have these in there just to make sure that these things are held in place properly. And we'll use this RTV to make sure that that we can get it apart after a heating cycle. So the nickel anti-seize compound, it's pretty effective for the temperatures that we're running at, but if you've ever worked with it, you know it's a little goopy and it stains your hands because of the nickel compound. Anyway, so we're going to get a little bit of this and we're going to apply it to the thread, and then this will then thread down onto our respective units, the nozzle inserts. Okay, so now we've completed the successful installation of our nozzle inserts. As you can see, both of our nozzles are installed. So we used RTV on the back to do a kind of a modest sealing surface back there. The pressure is pushing them outward against the shoulders, and then on the forward side, the nozzles come out, and we have these nuts that kind of keep things kind of in alignment, but they don't serve a big load function. Now, one thing that is worth mentioning on the design and implementation of these nozzles is because the nozzles are at an angle, they have to push the rotation of the system. So that angle, which is the beta angle, is very important to get that aligned. So these nozzles, when we fabricated them, they had to be marked so we know which way the lean was on the nozzles. And the way that's done is there is a small scribe mark that you can kind of make out on the nozzle. You can kind of see it right there. And that direction, that scribe mark, indicates the direction that the nozzle, when installed into the face, will rotate. So that nozzle, that mark right there, indicates that it'll push the Turborocket this way. And this one should be the other side. You can kind of see its scribe mark there, and so it'll push it that way. So that's how that's aligned there. And then another thing worth noting is on these hold-down threaded fasteners, which is a 256 socketed cap screw, we had to do a little cutout on that nozzle ring on the nozzle nut so that it can clear the bolt that'll hold that down. So that's not a real good design practice because you don't want to have something that aligns and then have a threaded fastener that has to come out correctly in the rotation. So I kind of did a kind of a custom fit on these to make sure that these would clear. But in practice, you don't really want to design something that way. Anyway, the nozzles are now installed, and we can assemble the rest of the Turborocket Mark 6 assembly now that we have our nozzles installed. So one of the technical challenges associated with building the components for the Turborocket engine is setting the correct beta angle, or the nozzle angle, relative to the axis of rotation for a particular Turborocket engine design. Now, in a typical Turborocket engine design, the beta angle is relatively small. It might be easily less than 5 degrees. In this particular design, the beta angle has been designed and set for 3 degrees. That's pretty small. That isn't something that is you can just easily set with like a protractor or something. You really need measurement tools to do that. And so I experimented with a variety of approaches for making the correct bend angle, for the tooling to make the correct beta angle in these nozzle inserts. So as mentioned, these nozzle inserts are actually fabricated from 18/8 bolts. That's an 18/8 stainless steel that machines real well. And so these little short bolts, that's a 1/2 inch with a UNF 20 thread on it, and also the same with the little nuts here, which I use to make these retainer rings. But the nozzle bodies themselves are machined down from the basic 1/2 20 bolt, and then we can put the correct beta angle into that machine down bolt nozzle insert. And so in the Turborocket engine, the nozzles fit flush or orthogonal to the face, to the inside face of the Turborocket engine combustion chamber. And then, so they stick out orthogonally to this outside face. However, to avoid scarfing of the nozzle face, the end of these nozzle inserts is machined at an angle, at the beta angle. And it's kind of, I don't know if you can quite see it there, but there is a bevel across that surface. And that's so that the nozzle is actually orthogonal to that carved surface as the nozzle goes through the nozzle insert. So that's how we put the nozzle angle, the beta angle, into the nozzle insert part. But then the question becomes, well, how do you actually do that? So I experimented with a number of different approaches. Most of them failed. Here's one I tried. I gripped it in a rotary table, and I just couldn't get the gripping force on this approach. I ended up trying a couple of other approaches, and I ended up settling on actually 3D printing a tool that's basically this ring, but it has an insert, or it has a space down in it that is at the correct beta angle. I don't know if you can kind of see that down in there, but you can kind of see that edge is smaller than this edge over here, so you can tell that that there's an angle to the insert that is put down in this. So with this plastic insert, I could then take an aluminum piece, machine it to size such that it fits down into this tool, and then when this is clamped into the drill, the lathe three-jaw chuck, it grips onto this piece, and then we can plunge the holes into this aluminum piece at the correct angle, and then this solves the alignment problem, as well as giving us a strong metal piece that can take the heating generated during the machining process. Some of our other pieces couldn't do that. I've also cut relief slots in here so that the head can flex, and so it's kind of hard to see that down in there, but that hole is at 3 degrees relative to the normal surface here. So then we take this piece, and then we can take our nozzle insert, drop that into this fixture. It's kind of a little stiff here. Let's try this one. And then we can set this up in the lathe, and then the insert is at an angle relative to these parts, relative to the head when it's inserted into the lathe. Then we can do a trimming operation. It trims the head at the correct dimension. Then we're also all set up to put the hole in. So we can just drill the hole in for the throat, and then also put in the expansion ratio for the exit area of the nozzle. So that's how we machine those nozzle parts using this set of tooling pieces to produce the nozzles at the correct angle. And so if we need other angles, then we can make another aluminum piece, print out another plastic piece, a tool holder for the tool holder. Kind of a recursive thing there. See what I did there? Anyway, so that's how we made that. Now our nozzles are completed, and we're getting ready to move further along on our testing procedure.